Every time you stream a movie, every time you jump on a video call, you're plugging into a global network that is, believe me, straining at the seams. So today, we're going to dive into the absolutely mind-bending physics that keeps our digital world from collapsing under its own weight. Okay, get this. Every single year, the amount of data flying between countries, cities, and all across continents grows at a compound rate of 40%. That isn't just big, that's an exponential tidal wave of information, and it's putting some serious pressure on the physical backbone of our digital world. And that right there raises the big question. I mean, think about it. 90% of all the digital data that exists was created in just the last 5 years. So how on earth can our physical systems, the actual cables and networks, how can they possibly sustain this kind of relentless growth? Well, the answer didn't start with computers. It actually started with a really clever way of manipulating light itself. The solution was basically to create a perfect tube for light. Now, the physics behind this is surprisingly old school. It dates all the way back to the 19th century. It's this cool principle called total internal reflection. The best way to picture it is like skipping a stone across a lake, right? If you throw it at a steep angle, it just sinks. But if you throw it at a really shallow angle, it skips perfectly off the top. It's the exact same idea with light in a fiber. As long as it hits the boundary at a shallow enough angle, it doesn't escape. It just reflects perfectly back inside. So the light literally bounces its way down this tiny glass tube, completely trapped inside, able to follow curves and travel for just enormous distances. It's kind of like a hall of mirrors that stretches across entire oceans. But for the longest time, there was a huge problem. In the real world, it just didn't work. The light would just fizzle out. The big moment, the real breakthrough, came in 1966. A researcher named Charles K. Kao had this Nobel Prize-winning insight. He realized the light wasn't dying because of some flaw in the physics or the glass itself. It was dying because the glass was, it was dirty. He predicted that if we could make ultra-pure glass, we could send light not just a few feet, but 4 kilometers. And that, right there, changed absolutely everything. But okay, even with perfectly pure glass, new problems popped up. Once engineers started sending signals down these brand new, pristine fibers, they ran into 2 major enemies that threatened to scramble the data completely. The first enemy was something called attenuation. It's basically the signal just getting weaker and weaker. And the numbers back then were just brutal. In 1966, a light signal would lose 99% of its strength after just 20 meters. After 100 meters, it was basically gone. Compare that to today, where a signal can go the same distance and still have over 99% of its power. The difference is just staggering. The second enemy was dispersion. Just think of it as signal smearing. See, in the early, wider fibers, light rays could kind of rattle around and take a bunch of different paths. That meant parts of the same pulse of light would arrive at slightly different times, blurring the data into mush. The solution was the single-mode fiber. By making the core incredibly thin, we're talking less than 10 micrometers, you force all the light to take pretty much the exact same path, and that keeps the pulse super sharp and clear. So, with our enemies identified, engineers developed some truly ingenious weapons to fight back. These allowed us to both boost the signal's strength and preserve its shape over thousands and thousands of kilometers. First up, to defeat attenuation, we got the erbium-doped fiber amplifier, or EDFA, and this thing is a total game changer. Imagine it's a cheering crowd at a marathon. You take a special section of the fiber and you dope it with atoms of an element called erbium. Then you use a separate laser to pump up these atoms and get them all excited. So then, as our tired, weak data signal runs past, the excited atoms all cheer for it, they release their energy and give the signal a massive boost to keep going, all without ever having to stop or be converted to electricity. It's brilliant. But not all boosts are created equal. The old method, phase-insensitive amplification, was kind of like shouting to make a whisper louder. Sure, the whisper gets louder, but you add a lot of your own noisy breath. That's what it did. It added noise. But the new frontier is phase-sensitive amplification. This is more like a perfect magical echo that only amplifies the original sound, adding almost zero extra noise. It's a trick that operates at the quantum level, and the payoff is huge. The data capacity declines 4 times slower over the same distance. And what about fighting dispersion, that signal smearing problem? For that, we found a solution that sounds like it's straight out of science fiction, the soliton. A soliton is this special kind of light pulse that basically heals itself as it travels.
The physical forces that try to smear it apart are perfectly canceled out by other forces that pull it back together. So it's like a surfer riding a perfect, self-reinforcing wave that just never breaks. It holds its shape over incredible distances, which makes it an almost perfect way to carry data. So, with all these amazing tools, we've pushed our fiber optic networks to carry petabits of data. I mean, it's incredible. But as we get closer and closer to the absolute theoretical maximum, we're coming up against a final, fundamental barrier, one we just can't engineer our way around. Yep. Because even with perfect fibers, perfect amplifiers, and these flawless little pulses of light, we are slamming headfirst into a fundamental wall. There is an absolute, unbreakable speed limit to how much information a single channel can possibly carry. And that speed limit is defined by this really elegant equation, Shannon's law. It's one of the most important ideas in all of communications. What it basically says is that the maximum speed of your connection, its capacity, C, is all about a trade-off. It's a trade-off between how wide your channel is, its bandwidth, and how clear your signal is compared to all the background static, the signal-to-noise ratio. Now, what this curve shows us is absolutely crucial. You see, at first, if you boost your signal power, you get big gains in speed, in capacity. But then, see how the curve just flattens out? That's the tricky logarithmic part of the equation kicking in. After a certain point, you can pump in massive amounts of extra power, and you only get these tiny, tiny little gains in speed. You hit a wall of diminishing returns. And this is why. Here is the final boss, quantum noise. And this isn't noise from some faulty piece of equipment. This is noise from reality itself. It's the result of tiny, fundamental fluctuations in the vacuum of space-time. Even in a perfectly dark, perfectly cold fiber, this background hiss is always there. And when our amazing amplifiers boost our signal, they have no choice but to boost this quantum noise right along with it. It creates an unavoidable noise floor, a hard limit that physics itself imposes on our data. We can't beat it. So if we're hitting the absolute physical speed limit on a single fiber, how do we possibly keep up with that 40% annual growth in demand? Well, if you can't make the individual lanes on the information highway any faster, maybe the answer isn't about building a faster car. Maybe it's about learning to use the highways we already have a whole lot smarter. And we have already built an absolutely colossal physical infrastructure. I mean, just look at this map. This shows only the submarine cables that form the internet's global backbone. We have the capacity, but for a long time we've treated it like a finite resource to be owned and hoarded. This quote from Rajendra Singh at the World Bank just captures this shift in thinking perfectly. For decades, we've managed these resources, like fiber capacity, like they were plots of land. You buy a piece, you fence it off, and it's yours. But technology is now pushing us toward a new model, managing it like the sea. Right? No one owns the ocean, but shipping companies all use it together according to shared rules. And this whole manage it like the sea idea leads to some really concrete new strategies. It means we got to think bigger, like sharing infrastructure costs with energy and transport companies. It means we have to think smarter with things like dig only once policies that say, hey, if we're digging up the road for any reason, let's leave fiber while we're at it. And it means thinking more dynamically, using software to share network resources in real time, just like ships sharing the open ocean. It's a real shift from private ownership to a shared digital commons. So that kind of leaves us with a final thought, doesn't it? We've taken a 19th century physics trick, we've battled the enemies of the signal, and we've pushed our technology so far that we are now literally bumping up against the background noise of reality itself. So the great question for our future is this. Will our next massive leap in capacity come from yet another technological miracle? Or will it come from the simple but maybe much harder act of learning how to better share what we've already built?